And of course, thanks a lot to Renzo and the whole organizing team here, which so far managed to organize a really excellent conference, which I enjoyed here. So I'm going to speak about magnetohydrodynamic relaxation. And in the spirit of this workshop, I designed the talk for the other half of the audience, which probably doesn't know too much about MHD. So to my MHD colleagues, an apology, you will have seen many of these things before. And for all the others, I hope you learn something from it. Okay, so this is these are results of long-standing collaborations with colleagues in Dundee, Alex Russell, Durham, Anthony Yates, Glasgow, Simon Candelaresi, and David Pontin, who was previously in Dundee and is now on the other side of the globe in Newcastle, New South Wales. Right, so what is the motivation here? I have here a picture of the solar surface or the solar atmosphere. What you see is an X-ray image of the solar corona and the faint structures of loops. This is very, very hot plasma, which is aligned with the magnetic field lines. So this is one of the rare occasions where you can actually see magnetic fields. So this shows you that the magnetic field on the surface of the sun is, first of all, much more complicated than the magnetic field of the Earth. And second, it's topologically non-trivial. And as I will argue, there are braided magnetic fields in there. So just the setting, how do we describe this? And what I will use here is the idea of a magnetic flux tube, and I call a braided magnetic field in a magnetic flux tube a magnetic braid. So magnetic braid is a magnetic flux tube, so something diffeomorphic to a solid cylinder. And I assume that the field is non-zero everywhere in that domain. So we have a non-vanishing magnetic field component along the tube, right? So that generates a mapping from 1 foot point, and the surface here, you can think of that as the photosphere, the surface of the sun, or the visible surface of the sun, connecting one patch of polarity to another. Right. So this allows us to define a mapping from this place where the field lines emerge, which I call D+, that's cross-section, to D-. Such a mapping in itself has not much information unless we know how to compare the endpoints with the initial points of the field line. And we do this by choosing a reference field. So a second mapping, which gives us something to compare our mapping, our original with. And that mapping is often derived from a potential field. And so there are two reasons for this. First of all, a mathematical, the potential field in such a domain, which we require to satisfy the same boundary conditions, so the same normal component on these cross-section is uniquely defined. So this is a nice mathematical property. And the second property, which is important, is it's the lowest energy state which the magnetic field can take on in that domain. And so that makes it a kind of, from the physical point of view, also a natural choice. So often we will refer to this reference field as the potential field, but there's no principal reason why we couldn't choose any other field if we wanted to. Right, so once we have this reference field, we can define a mapping which I called here capital F, which goes first forward via F and then backwards via G. And so this gives you an automorphism of the disk D plus or the cross-section D plus. And such a mapping now has topological features, or you can define things like periodic orbits or possibly ergodic field lines and flux surfaces or topological entropy. Right. In most cases, we will, for simplicity, also straighten out this domain. So instead of this curved flux tube, we consider the straight cylinder just because that's easier. And in the straight cylinder, the potential field is also quite easy. It's just the homogeneous field in that direction. Right. Braided magnetic fields on the sun. Why are we interested in these? Now, on the sun, these fields are anchored in the photosphere. The photosphere is much denser than the corona, the atmosphere above. And it's turbulent. It undergoes a slow but turbulent motion. The field lines anchored in that photospheric plasma are moved with that plasma and eventually braided. And I indicated this with these blue arrows here. So there's a braiding going on, and in principle, this is continuously going on, which increases the energy of the field inside our flux tube. And eventually, something has to happen because the energy can't increase indefinitely. So some relaxation process has to happen. And this talk is mainly about the final state of this relaxation process and how we get there. This release of energy is believed to be important for the heating of the corona, and there's a long-standing puzzle for solar physicists that the corona, which is above the photosphere, is much, much hotter than the lower lying photosphere, although the main source of energy of the sun is inside the core of the sun. So you have this strange behavior that the energy, that the temperature drops at a certain level and then increases again. And the only explanation for that is that there is a heating process going on in the outer atmosphere of the sun in the corona. Right. So a little bit about the dynamics of these plasmas. The easiest or simplest description is that of magnetohydrodynamics, and here is a full set of equations. Magnetohydrodynamics essentially coupling equations for the fluid, the plasma, to equations for the dynamics of the electromagnetic field. And here the magnetic part of the electromagnetic field is the dominating one. And correspondingly, we have an equation here, oops, a bit too fast, an equation for the evolution of the magnetic field. This is so-called induction equation, which has two terms on the right-hand side. One, which shows you the interaction with the flow of the plasma, and a second one, which is a dissipative term. This is the kind of resistive or ohmic heating. The second term is comparatively small compared with the first term on the right-hand side of that equation. And that ratio is measured by the magnetic Reynolds number, which is quite high. So the first term on average in general is many orders of magnitude bigger than the dissipative term. In the equation for the motion of the plasma, we have the J cross B force, the Lorentz force, which describes the effect of the magnetic field on the plasma. And so these two together, these two terms here, describes the exchange of magnetic energy between the magnetic field and the kinetic energy or the velocity field. We have two dissipative terms here, the viscosity and the resistive term, and they eventually show up in the equation for the energy density as well as source terms. So there's energy transferred from kinetic to internal energy and also from magnetic to internal energy. So if you want to describe things in very rough terms, in terms of energy, we have three types of energy here: magnetic, kinetic, and internal energy. There is an exchange between magnetic and kinetic energy which works even without viscosity and without resistivity. And then there is a dissipative loss of magnetic energy via resistive heating and a dissipative loss of kinetic energy via viscous heating. And eventually all the energy which has accumulated in the internal energy can be moved either via heat conduction or via radiation to the outside. So this is a rough scheme of how magnetic relaxation can happen. Now, I mentioned that the magnetic Reynolds number is extremely high. So the resistive heating is typically very, very low, or the process of losing energy via that channel is very, very slow, right? So that motivates that people look at the ideal evolution, so they ignore this resistive term altogether and look at the evolution of the magnetic field without resistivity, and that's called ideal dynamics. And then your induction equation, which I wrote up there, gives you a conservation of magnetic flux. This is the so-called Alfvén theorem, and if you like differential geometry, you can write this in terms of the Lie derivative of a two-form magnetic field is a two-form, and that gives you the conservation of the integral Lie. And that means that your magnetic field is transported by a flow, a diffeomorphism. So at any time t, you can pull back the magnetic field under this mapping and get to the magnetic field at your initial time. And this mapping is the flow of the velocity field. So here's just a sketch how to look at things. If you think of any kind of flux tube in your domain and you measure the flux through some cross-section, then that flux is preserved in time during the evolution, while the flux tube of itself, of course, can be deformed in an almost arbitrary way. Right. Now, this cannot be the whole story, because we know that from observation that the topology of these fields change every now and then. There are big eruptions on the sun and of magnetic fields. And so reconnection has to happen. And now I have to disappoint all the kind of topologists in this room, because the reconnection which is happening here is not of the simple kind of surgery type reconnection. It's what I call 3D reconnection. So you have two flux tubes here, like the red and the blue one, and they can interchange their connectivity in the way showed in the top row.
Gunnar,
yeah.
Please keep the mic
closer. Okay. The top row, and the view from the top looks very much like the typical anti-parallel reconnection, but it is not anti-parallel, and the flux tubes develop rise, and there's even a production of twist in this process. So the final set of flux tubes have additional twist in it. So this process is different from the surgery or anti-parallel reconnection, and it's a generic one, so this is not something unusual. This is a typical situation. It has to be the typical situation because the anti-parallel reconnection requires null points, and in my braided magnetic field, I don't have any. And the process adds a little bit of twist to the flux tube, and that can be measured via the helicity. So if you write down the evolution equation for the magnetic helicity, A dot B, you find, if you integrate over the volume, that the source term is the term E dot B, the electric field, times B. Now, this electric field is also the electric field which is responsible for the reconnection process itself, for triggering the reconnection. So this electric field here is essential for the reconnection to happen, but at the same time, it's a source term of the helicity. So you can't have reconnection without this term, at least not in the 3D version. And so there is a production of helicity in this process. Now, that is the bad news. The good news is the production is not very big. And that is due to two effects. First of all, the volume in which this happens is small compared to the overall domain of your flux tube. So this process happens in a rather small area between the two flux tubes, and it happens only over a very short period. And the smaller your resistivity is, or the higher your magnetic Reynolds number is, the smaller this volume becomes. And so for very high magnetic Reynolds number, this term here, although non-vanishing, is small. And that is what we heard yesterday, I believe already, that in the limit of very, very high Reynolds number or vanishing resistivity, we get a conservation of magnetic helicity. So on the time scales of these processes, this term is much smaller typically than the helicity itself. Right, so minimum energy. Which states do we reach with our relaxation? We want to find the minimum energy states of the magnetic and the kinetic energy. We can set the velocity to 0, that minimizes already the kinetic energy, and then apply a variational principle to the magnetic energy. And we have two extreme cases. Either we can use the full resistive evolution and do our variational principle with a resistive term, then the end state is one which has a vanishing curl of the magnetic field, so no currents in our system anymore. That's kind of obvious that that has to happen because any current would dissipate away. But that is also not an interesting system because it takes a very long time for these resistive relaxation to take place. And it's also worth mentioning, because we had this yesterday, if you have a multiple connected domain, then the final state is a harmonic field. If you, on the other hand, ignore the ideal, the resistive term and look at the variational principle applied to an ideal plasma, then what you get is that J cross B, or so the curl of B cross B, has to vanish, and that gives you so-called nonlinear force-free fields. Now, nonlinear because this proportionality factor lambda here can depend on x. It has to be constant along field lines, but it can depend on on individual field lines, and that makes this equation a nonlinear condition and quite tricky to handle. So both these extreme cases, are not what we are looking for. The resistive case is way too slow to explain what we observe, and the ideal plasma is also inconsistent with the observation, because if it were an ideal plasma, then our continuous braiding would increase the energy indefinitely. We would have no heating of the corona, and this is inconsistent with the observations. So something in between has to happen, and that in between is motivated by the conservation of magnetic helicity in the reconnection process. So if we assume that the magnetic helicity is conserved and do our relaxation process with the constraints that we have magnetic helicity conserved, here this is a Lagrangian multiplier, then we end up with the condition that curl B is lambda B, but now lambda is a constant. And the result holds even if the domain is not simply connected or open, and that is the case which we were looking at here. Now, of course, we find these linear force-free fields as the minimum energy states, but that doesn't tell us necessarily that these states are also accessible via the relaxation. All what we tested here is what the minimum energy state would be if it can be reached. So which linear force-free fields have the lowest energy would be a natural question to ask. And we know that there are quite a number of linear force-free fields in any given domain, typically infinitely many. And so one has to look at individual domains and see which linear force-free field has the lowest energy. Before I come to that, I want to also mention an important inequality, and that is, I think, quite helpful to see this inequality in given our discussions in the previous week about complexity and topological complexity and energy. So this inequality, which was stated by Arnold in the 70s already, gives you a relation between the helicity, or the absolute value of the helicity, and the energy on the right-hand side. And the constant C depends only on the geometry of the domain. So helicity is the lower bound for the energy. You can, to give you an idea how this can be applied, the helicity is invariant under ideal relaxation, so under diffeomorphism, if you want. So if I have a here, if I have a flux ring which has zero helicity, so not twisted in any way, then this left-hand side is zero. If I relax that flux ring, I can reach a lower energy state, and indeed I can reach an energy of zero by shrinking this flux tube to almost a point, and at the same time stretching it out along the z-axis, so that this works even with a volume preserving diffeomorphism. I can't do this if I have some non-vanishing linkage or non-vanishing helicity in my domain. So if I have a link here, a Hopf link of that type, and I try to relax that, at some point these two rings crush into each other. And since I allow only ideal evolution, they can't undergo reconnection. So the lowest energy state becomes something similar to this figure here, where you can see that the one ring has spread out around the other one in order to minimize its energy as far as possible, but then it can't go any further. Right. So this equation gives you a relation between the energy, which is of geometric nature, and the helicity, which encapsulated some topological information. And I think that is the best we can do. In general, you will always have that the energy will involve geometric properties, and the best you can do is to find such inequalities. However, that doesn't mean that this is the only inequality of that type, and there could be other measures of the topology on the left-hand side. And people like Michael Friedman, for instance, wrote down a similar equation where on the left-hand side is an expression with involving the crossing number. Right. If you use our previous result and plug in the linear force-free fields, oh dear, into this equation, you find that they get you the same energy integral on the left-hand side with a factor 1 over lambda. That is the eigenvalue of your linear force-free field. So the constant C is actually the minimum eigenvalue of the curl operator in the domain. And so people have looked at various domains here and have calculated this minimum eigenvalue for these domains. Jason, for instance, is he here? Yes. Many years ago, looked at the sphere, and you can find that you get a factor 0.4451 here, as a cube gets you a similar number. And you can even look at domains which are not simply connected. So here is the solid cylinder with the periodic boundary conditions. And you can also find that there is a minimum ratio of helicity to energy in that domain. Right. So this idea that helicity is conserved and that we reach linear force-free field in a relaxation is the basis of a famous hypothesis by J.B. Taylor, put forward in the 70s as well, that the relaxation of a toroidal plasma, the reversed field pinch, leads to a linear force-free field, conserving the total helicity and the toroidal flux. The toroidal flux, again, would be our harmonic field in our domain, or the reference field. The assumption here is that we have a very efficient turbulent process which generates a lot of reconnection, and so our braid, which is essentially has infinitely many strands, can reconnect quite a lot, and that leads so it can find the lowest energy state, and this should then be a linear force-free state, and the total helicity and total toroidal flux are the only invariant. So the first assumption is a pretty good one, that we assume that there's a turbulent process in that plasmas of that high temperature are typically turbulent. The second one we already proved mathematically, that minimum energy states are linear force-free fields. So that's a good assumption. And the last one is maybe the most difficult one or uncertain one, whether total magnetic helicity and total toroidal flux are the only invariants. Total toroidal flux, one can show that this has to be an invariant, but the total magnetic helicity is the only invariant. That's not for sure. And so we try to test this in simulations, and for that we set up magnetic braids. And we did this in the following way. We used a long box. We put in a background magnetic field, a homogeneous field, and then we superimposed to that background magnetic field regions of twist. And these are indicated here by these blue loops. And these are finite regions in the domain where the field lines are twisted, and that generates, for at least 3 of these field lines, there are infinitely many in the domain, a braid, right? And we kind of, in this way, model on a braid our magnetic field. For this example, we used the pigtail braid. So the braid word is the sequence of left and right hand twists as we go upward along the magnetic field. We can, in principle, generate arbitrary braids in that way, right? Here on the left-hand side, I plotted a set of field lines, and they are connecting the lower and the upper boundary. Half of them start at the 2 locations in the lower boundary. So this is here for the yellow ones and here for the green ones. And another 2 sets start at the upper boundary, these orange ones here and the red ones. And I follow these field lines along the magnetic field to the other side. Why I've chosen these 2 sets will become clear in a moment. On the right-hand side, I show you a plot on the lower boundary, a cross-section of the lower boundary, and what I plotted is the integrated current along any given field line. So each point in this domain here corresponds to a field line, and it is colored according to the value of the integral of the current along this field line. Why have I chosen that? Because in the end, if we reach a linear force-free field, that current corresponds to the lambda of the eigenvalue of that linear force-free field. But this integral is also defined for all the intermediate stages of the evolution. Okay, so now I let this thing evolve, and what you see is that the field simplifies, and then it simplifies into a configuration where we have two twisted flux tubes inside our domain, one with right-hand twist and one with left-hand twist. And now you can see why I've chosen these particular starting points, so that you can easily recognize that there is now a simple twisted tube in the domain. And if you look at the corresponding evolution of this quantity, of this lambda star, you see the two peaks, a blue and the red one, for the positive and for the negative and positive value of lambda star. So what does that tell us? It tells us, first of all, that we don't reach linear force-free field. Obviously, there are two different values of lambda here, positive and negative. And that, of course, was a puzzle to us. So the Taylor relaxation hypothesis seems to not work in this case. And we, of course, tried a lot of different things to check that we haven't made any mistakes here. And in particular, we changed our boundary conditions from a line-tied to a periodic case. So now we look at the same evolution in a periodic box, and we see an even more extreme deviation from the linear force-free field. The line tying has kept these two flux tubes together, and now they can separate as far as I want, or as far as the box allows. If you compare this with the line-tied case here on the right. Right. So we tried various other things. We, for instance, used a braid which has only positive helicity, so where our twist regions are all of the same direction. So this inserts a total helicity. We have a non-vanishing total helicity in our field. Previously, the total helicity was 0 because we had as many left-handed as right-handed twist regions. Now we have positive helicity, and what happens is something which is still not a linear force-free field, but kind of closer. So first of all, it has the right symmetry. It has now an axis symmetric configuration as a final state. And second, one could, with a bit of goodwill, identify the inner region as roughly constant lambda. So the relaxation has maybe partially worked, and there's still a problem towards the outside. But it's also clear that the boundary conditions are not consistent with a linear force-free field, because at the outside we have only a homogeneous field, so the total relaxation process happens only strictly inside the domain, and the lambda therefore has to drop to 0 somewhere, and it does so with an undershoot here. It becomes negative, and before it reaches the 0 value at the boundary. Right, so first conclusions, the Taylor hypothesis does not match our results, and the total helicity and the toroidal flux are preserved, so that is correct, but the field is a non-linear force-free field. And so we are looking for further constraints which guide this relaxation process. And there are several different explanations as why this could happen. And my favorite one is here, the second one, the dynamics of this process preserves some other invariants which we haven't considered here. Right, and in order to investigate this, we set up a new quantity, the magnetic field line helicity. It's defined as shown here, so it's an integral of the vector potential along any given field line. And in general, this function is not gauge invariant. You can make it gauge invariant by imposing the right boundary conditions. So you use the this condition here on a vertical line on the boundary, which gives you which is motivated by the fact that we don't want any magnetic flux outside the domain to be measured by our vector field. And the second condition here is one of consistency of the vector potential, the tangential component of the vector potential with the vector potential of our reference field, our guide field, which is called a P here, P for the potential field. If you use these definitions, then you get a consistent interpretation of this as the relative helicity density, so to speak. So relative helicity is defined here. That goes back to work by Mitch Berger field in 1984, and our gauge condition means that our field line helicity integrated over cross-section is exactly the relative helicity in that domain. Right, this quantity, which is now defined on a cross-section, has some nice properties. So it uniquely defines the topology of the braid, and that I find the most surprising result, in that you only need the information on a cross-section to reconstruct the whole topology of the braid, right, in the whole volume. Only up to deformation, but the vector field in the whole domain. It's invariant under ideal flow, and it changes only due to magnetic reconnection. So if you see some change in this quantity, it's always due to reconnection. Right. So if you plot this instead of your force-free field parameter and let this run, you see something similar for our first example of the pigtail braid. So the plot for this field line helicity looks kind of similar to the one for the current density, or integrated current density, the lambda star. Now the choice of colors is maybe not the best one here. So there's a left-right symmetry, or anti-symmetry, I would say here. But you clearly see the same behavior as before, the separation of the structure into two flux tubes. Right, and here is my best explanation as to why this is happening. So we need quite a lot of turbulence in any such process to relax the field to the minimum energy state. right? So ideally, every field line should get into contact at some point with any other field line to exchange twist and kind of minimize the energy over the whole domain. So in this process, we get a number of different reconnection processes or individual situations. And I started here with one where I have two field lines connecting regions of different twist. That's very typical if I have such a braid with left-handed and right-handed twist regions. So I, for instance, have this field line here, which connects a region where I have right-handed twist with a region where I have left-handed twist. So along this field line, the A parallel, which is important for our integral, A parallel dl, our field line helicity, that will be greater 0 down here and will be less than 0 up here. So if I integrate along this field line and assume these two regions are roughly of the same size, then I get a value somewhere close to 0. Right? I could reconnect that field line with another one, which is of similar nature, right? And this time I have negative twist here, down here, and positive up here. Again, the field line helicity of this field line is something close to 0. If I do this, I separate these two regions and get two field lines, one with negative field line helicity and one with positive field line helicity, because now this one here is a field line which has left-handed twist down here and left-handed twist up there, so that adds up and gives you a finite value. And similar on the right-hand side, the two contributions add up and give you a finite value. Right. Now, that, of course, is not the only option which I have. And I could start with the end state here and look at the reverse process. So I start with a field line which initially has a high value of integral A parallel dl, positive 1 and one with negative 1. Right. And if I reconnect these, then I end up with two field lines which have roughly 0 field line helicity, because now I connect regions with opposite twists. That is essentially the process which we want to have in our relaxation in order to reach the lowest energy state. Remember, for our first example, the total helicity was 0, so we want to cancel out as much as helicity, much local helicity as possible. However, if these are twist regions, then this second process is much less likely to happen. And why is that? Because, oops, sorry. This twist here, both negative on the same field line, means that there should be a current along this field line, a negative current. While for this field line here, there should be a positive current along the field line. Now, currents of opposite direction repel each other. So the reconnection here is rather unlikely to happen because it has to go against the energy, against the forces. While this is not the case in the upper process. So there's a bias in the reconnection processes here. This second case is much less likely to happen than the first one. And that explains why the total helicity is conserved, so both processes conserve the helicity, but actually our relaxation leads to a separation of the local helicity in the domain. I'd say there's a physical argument as to why that has to happen. Right, this is another set of simulations which also try to look at the symmetry of our final state. What you see here is in each column a simulation at 3 different times, t equals 0, t equals 100, and the final state at about t equals 300. The first column has a background field, which is a linear force-free field with a proportionality factor alpha equal 0.001. So that is very, very close to the homogeneous field. Essentially, the first column is the example which you've seen already. Right? Sorry. And that in that case, the initial braid splits into these 2 flux tubes of positive and negative twist. I then increase the background field, the eigenvalue of the background field. So I insert much more twist, positive twist, into the whole configuration. And as you can see, there's a transition at about alpha equal 0.05 from the separation into 2 flux tube into a symmetric separation. So in this case, I have much more positive helicity in my domain, and correspondingly many more cases where the currents have the same direction in the reconnection process, and that allows a relaxation to a linear, or better relaxation to a linear force-free field. And correspondingly, we now see a field which has lower, in the end, lower values of lambda, and also the right symmetry. Right, and that takes me to the end here. So I hope that I convinced you that there is more than linear force-free fields to the relaxation, and we have to consider additional constraints to our relaxation process. And a first improvement would be to consider the areas for which the field line helicity has certain values. So a function like this one here, phi of A, which integrates all the flux for a given value of a field line helicity. And if you take this and assume that that is constant, and if you do this, you get an improved hypothesis which better represents the final state. I don't think that is the final answer. We still need to work on this, but that is the state of affairs at the moment. And I would like to end with that. And instead of a summary, I propose here a challenge to the community. We need better or more measures for higher order linking or knottedness in fields. For continuous fields, which can be applied to MHD or vortex dynamics, I'm aware, of course, that there is this result that helicity is currently the only invariant which is invariant under volume preserving diffeomorphism. But even if you come up with an integral which is not invariant but still has a non-vanishing value for any diffeomorphism, that would be interesting for these kinds of inequalities, and they can help us to learn more about the dynamics of magnetohydrodynamic relaxations. And with that, I would like to end and thank you for your attention.